Let's not waste any time, huh? Got a little bit of work to do. Here we go. Woohoo! All right. Okay, so we started off our new unit, getting everybody on the same page so that we could talk about functions, right? We want to make sure that we're talking about functions. We're on the same page. Ray, glass down. I don't want to see your glass on your iPad. No glass on your iPad. Covers. Get your cover? Oh, thank you. Okay, that was very shiny. You have a very shiny cover, Ray. Thank you very much. Appreciate that. Okay. So, functions, right? Any, relation that we have here where an x has its own assigned y. It's okay to have, the same y as a different x. What we just can't have is one x have two different y's, right? We can't have an input have two different outputs or we don't have a function. Okay, so this lesson, we're going to just take a snapshot preview of some of the types of functions that we're going to be talking about in Algebra 2. And these aren't all of the ones that we're going to talk about, but these are some of the ones we're going to talk about. Now, to be fair, some we're going to do a deeper dive on, and some we're just going to kind of swim across the surface on, like linear functions. We did a pretty deep dive on linear functions. We connected linear functions to arithmetic sequences. We talked about how common differences and slopes are the same. We went back and reinforced 3 different formats of linear functions: standard format, slope-intercept format, point-slope format, right? And those are going to come into play as we talk a little bit more, but we've really kind of done our deep dive on linear functions. Another type of function we're going to look at is an absolute value function. Okay, this one will be one we sort of swim on the surface of. It's not that complicated. We're going to do a deep dive on quadratics. That's going to be where we head next. We're going to go deep, super deep on quadratics. Okay. We're going to talk about some square root functions. That's a type of function. We're going to talk about exponential functions, which we kind of started a little bit, right, with our geometric sequences, right, and our common ratios and all of that. We're going to be looking at reciprocal functions, and that's what I got for you for today. We're also going to be looking at polynomial functions. We're going to be looking at rational functions. These are things that we need a little bit more explanation for. We'll be looking at logarithmic functions. So there are different types of functions still to come. Those are all kind of for next semester. But we're going to just kind of get an idea of how this idea of functions produces with different math, okay? And so you can see the title of this lesson is Parent Functions, okay? And one of the things that I want you to understand is that there are a lot of similarities and some differences to all of these types of functions that we're looking at. And so one of our goals is going to be to find those similarities and differences and use them to help us gain a better understanding, okay? So we're going to start with some parent function information. And the way this lesson is going to work is we're going to talk about the first box here, the parent function, and then you're going to go online in a little bit, and there's going to be some examples for these that you are going to work on as part of your classwork/homework. And there will also be some inputs given to you that I specifically chose, and you're going to use those inputs and these function rules to come up with the outputs and then create a picture that you think is what it's going to look like, and then you're going to check that picture against Desmos. Okay, that's the idea of what we're going to do here. Okay, so let's just start with a parent linear function. And so the linear function for a parent is f of x equals x. This is a one-to-one function. Output equals input, right? That's what we're saying here. Okay, and so if we were to do some examples, we're just going to do a little squiggle through here and a couple of squiggles down the bottom. We're not going to use those boxes. But like if I gave you these inputs, -2, -1, 0, 1, and 2, and I asked you to take each one of those inputs and drive them through this function machine right here, you would take your inputs, drop them in for x, and I'll get your output just like that, right? Yeah. So we take a -2, we drop it into our function machine, and out pops a -2, exactly, right? And so our input and our output is -2. We take a -1, we drop it into our function machine, out pops a -1, because this is a one-to-one. We drop a 0 in, what do we get? Okay, 0, and then a 1, and then a 2, right? And then we can take these coordinates that we got by dropping them into our function machine, and we can start plotting points over here on the tail side of our function. Head side of the function, head side of the function, tail side of the function to draw the picture, right? So then we start plotting some points over here. We go, okay, well, -2, 2. All right, well, again, x is on the left and right, y is on the up and down, so -1, 2, -1, 2. Then we put a point there. -1, 1, we put a point there. 0, 0, we put a point there. 1, 1, we put a point there. 2, 2, we put a point there. And then we can see that these seem to be connected in this type of pattern that we have going on here, which of course we know as a line, which makes a linear function. Okay, now listen. Today, I'm going to expect you to find the outputs for the inputs and plot those and use those to create your graph. In other words, you can't shortcut it with rules that you previously learned. You've got to plot the points and use the points to draw the graph. So every one of your examples today will have inputs that you need to find the outputs, and then those inputs and outputs need to be reflected on your graph as best as possible, okay? Now, sometimes you're going to have weird fractions. They need to be in the general area of where they should be, okay? All right, so like if you've got a fraction, you've got to plot 1/2. I shouldn't see that like way up here or way over here, okay? I should see it in between 0 and 1, okay? Try to be in the middle, right? That would be the idea. Now, one other thing that I do want to make a note of here with your linear function, this is input to the first power. And if you want to just make a little note there, that's the first power. That's what makes a function linear mathematically, is when our input here is being raised to the first power. That's how we get a line function. So a line function is when your input is to the first power. Okay? And then we're going to talk about domain and range for each of these. So what would be the domain for this one from the x values? This is a line we drew. We use the points to create the line, but the line is a continuous function. So then it would be all real numbers. Okay, so all of the graphs that we do today are going to be continuous functions. We're going to use the points to create continuous graphs. So then what's our range for this one? Yeah, also all real numbers, right? Because this goes all the way up and all the way down. Linear functions. That should be pretty easy, right? Okay, so you'll get the other examples from Google Classroom when I post those up there for you to work on. Okay, all right. Let's talk about absolute value functions. All right, so the absolute value function is going to look like this. Your output is equal to the absolute value of your input. We can even jot that up here. This is the absolute value of the input. Okay, so I'm going to give you some inputs here. So I'm going to give you an input of -3 and an input of -2 and an input of -1 and 0, and then an input of +1, +2, +3, and we won't use the last box. All right, so let's take a -3. Let's drop it into the box. Let's, and then what's our +3, right? Because remember, what these bars here, and this is not, we're not looking for the determinant of a matrix, right? Looks like it, right? But this is our absolute value. What we're saying is how far is -3 from 0 on a number line? That's what we're saying. And distance, as we learned in geometry, is always a positive measurement. That's why absolute value is always positive. So if I drop a -2 into my absolute value, what am I going to get out? +2. If I drop a -1 in, what am I going to get out? +1. If I drop a 0 in, it's 0 distance from 0, sure. If I drop a +1 in, I'm still going to get +1 out, and then +2, and then +3. Okay, so put those points on your graph, all right? And then let's see what you think this graph might look like. Go ahead, give it a try.
I think this is going to be like or a triangle.
Come up with that picture right there. Now, let's be clear about something, right? There is a constant change going on here, right? It's over 1, up 1, over 2, up 2, over 3, up 3, over 4, up 4, like that, right? So that constant change produces a straight pathway, because that's the definition of a linear function, right? We have a constant rate of change. The only thing is that we now have no negative values for our y's, for our outputs. We only have positive values. So it's almost like we took the parent function of the linear and bent it up that way. So we just took that stick and bent it up this way so that we wouldn't have any negative outputs, okay? And so that's what our absolute value does for us, is it forces us almost like a reflection off of the water. It's like, boing, and it bounces off. We can't have any negative outputs. Okay, why don't you try to write the domain and the range? Let's see if you can come up with them. Go for it. Again, dealing with continuous graphs. Your domain and range.
Oh,
right? So from a left and right perspective, this graph stretches from negative infinity to positive infinity, so we can just say all real numbers. However, from a range perspective, it bottoms out at 0, and then it's everything greater than 0 from a range perspective, right? So if we were going to, again, do those boxes where we kind of drew our limits on there, right, this would be a 0 down here. Well, we'd have positive infinity up here, positive infinity over here, and negative infinity on the other side. Good? Okay. Absolute value function. There you have it. Okay? All right. Quadratic function. Quadratic function is your input to the second power. All right, so then that's going to look like this. Your parent function for quadratic is input squared. All right, so if I gave you a -3 and I asked you to take that -3, drop it into the function machine, process the math, and kick an output,
you're getting 9.
What kind of a 9? Positive or negative? You're getting positive, right? Because look, we're replacing this right here. So we're getting -3
Times -3
squared, right? That pause is in there, and so this is -3 times -3, which is going to result in a positive 9. Okay, so then if I gave you these, okay, and then we won't do this last one. You go ahead and fill in the rest of the inputs and outputs. Go ahead and do that first. Okay, you got them? Okay. Inputs and outputs should look like that. All right, now let's plot our graph, and then let's see what you come up with for a picture. Go ahead, give it a try. We can wing it for the last one.
You're gonna have to do a trick.
Should have come up with something that looks like this right here. Now, this is not going to be a straight line, right? Because we don't have a constant rate of change, right? If we go to the right 1, we go up 1. We go to the right 2, we go up 4. We go to the right 3, we go up 9. And so by nature, that forces this to have this kind of curved, increasing, non-straight lined shape. All right, let's talk domain and range for a quadratic parent function. Okay, what's the domain?
All real numbers.
Sure, all real numbers again. And then our range?
Y is greater than or equal to 0.
Y is greater than or equal to 0. So you're taking your input and you're squaring it. Okay? So that's our quadratic is input to the second power. Good so far? This should be easy. All right. Let's talk about square root functions. Okay, this one, ready for this, is input to the half power.
Square root. Oh, these are the worst.
Jack. Yeah, this is where your calculator might come in handy. Maybe, I don't know, we'll see.
For some.
Right, you don't know.
Right, but here's the idea, right? We're going to take our input, we're going to raise it to the half power. We'll talk more about fractional coefficients later, but that is the square root of, or hey, right? The question this sign asks us right here is, hey, what number times itself gives me, right? That's the idea. Whatever's inside my, what's this called right here? Anybody remember what this is called?
Square house.
No, that's a special name. No, it's not the Square House.
When they leave it, they shop
I think that's going to be your new nickname, Square House. Okay. What's this called? Begins with an R. No, that's not the fancy name for it. It is the kind of, like nickname, root name. RAD. The Radical. Hey, do you remember what this one's called inside? That's the radicand. Like divisor and dividend, that kind of thing. Okay. All right. So then, let's see. We won't use this one, and we won't use this one, and we won't use this one. All right. So I'm going to just give you some inputs, and I'm going to let you go to town with that, and we'll see what you come up with. All right. So why don't you go ahead and do your outputs, your graph, your domain and range. Like, you do the whole thing. Let's see what you got. Go for it.
Hey.
Here's what you should have come up with here. Okay, so as of right now, important, we currently are not able to take the square root of a negative input yet.
Why yet?
Because we will be able to soon.
Sweet.
But we can take the square root of these other numbers here, and I gave you some easy numbers to square root, so gives you a couple points to kind of anchor on. But you'll notice that that's why you've got no inputs over here on the left side of the y-axis, because you can't have the input of a negative number. Okay? And so that's going to make our domain all of the values greater than or equal to 0, and at the same time, our range all of the values greater than or equal to y. Now again, these are this is not a constant change of rate, so these are growing exponentially essentially, and so you've got this curved graph going here, right? Now, again, if you think about it from an absolute value perspective, we also can't end up with a negative out here, right? With this particular graph, when we take these square root numbers, we can't square root a negative value inside. And if we square root a positive value, we're never going to end up with a negative value out here, because the only way we can get a negative value is to have two different signs, and you can take the square root of a number with two different signs. They'd have to be the same sign. And so in that case, that forces all of our range to also remain greater than 0. And so we're refined to quadrant 1 here with our square root graph. Make sense? Kind of logical. Okay? Good so far? Okay? All right, then. Let's talk about exponential graphs. Exponential graphs. All right, so exponential graphs is where the input is the exponent, which we've started to kind of see these, right? We started talking about these with our geometric sequences. Now, this one's kind of funky because of this right here, okay? So this is called the base of the, whoops, I drew my arrow to the wrong place. Hang on, sorry. Okay, here we go. This is called the base, and it can/will vary. So we could have a lot of different parent functions for exponential functions, because we could have base 2, base 3, base 12. We could have a lot of different bases in there. We could even have negative bases in there. And we should know that because when we were writing these, this was the common ratio. Remember writing that? It was the common ratio to the power, right? And then it was a, so it was a sub 1 times r to the n minus 1. Okay? Okay, all right, so let me give you some inputs for this one, and let's see what you can come up with for a base 2 parent function. Again, these will vary, the bases will vary on them, but the graph remains very similar. So let's do -4, -2, 0, 1, 2, 3, and then we'll just not use these last two. Sweet. I want you, for this entire lesson, to work in fractions. not decimals. Okay. Go ahead. Let's see what you got.
How do I even do that? How do I convert it to fracking form?
All right, let's do a quick review on negative exponents. All right, so we'll squeeze it in right up top here. So if I had let's see, let me change my colors here. So if I had 2 to the negative 4th power, that's going to be the same thing as I put this over 1, and then I flip my 2 to the bottom to change my exponent positive. So that's going to be the same as 1 over 2 to the positive 4, which is going to be 1/16. If you need more on that, we can talk about that. If that blows your mind and you're like, why that is, then we can talk about that at another time. But you should know how to work with that. Okay, so we'll give you the 1/16 and then you can do the rest. Go ahead. What you should have come up with? Well, your exponential base 2 parent function.
Wait, will it ever intersect x-axis?
Right, because it's going to continue as we continue to we continue to decrease that exponent number, -6, -8, -12. It's just going to create a smaller and smaller fraction, but it'll never get to 0, right? So our y needs to be greater than 0, but it can't be equal to 0, and that's why that's important that you don't have an or equal to underneath that on the range. Yeah? All right.
Wrong.
Good there? Okay. We kind of looked at these just a little bit, so we're gonna do a deeper dive on these as well. All right, so then let's talk about the last one I have for you today, which is a reciprocal function. All right, and a reciprocal function is your input in the denominator. So a parent function for reciprocal is going to look like this: 1 over x. Okay, let me give you some inputs, and then I'm going to let you go to town on this one a little bit, and we'll see what you come up with. So this is -4, -1, -1/4, 0, 1/4, 1, 4, and we won't use this last one. All right, let's see what you got. Find yourself some points to plot and see if you can come up with them. Go ahead. Right here. Okay, let's think about it for a second, though. Does it make sense?
No.
Well, if you think about it for a second, we can't divide by 0 in any situation. In any situation, we can't have an input of 0. That means we can never have an x value on the x-axis. At the same time, could you think of any potential number that you could put in here that would produce 0 for the output? What?
Yeah, I think Brad's got some.
Could you? Pick a number. Let's start with a simple number. Put a 3 in there. What's the output going to be? 1/3. Put a 5 in there.
Oh, you can't.
1/5. 1/7. 1/112. If you put a negative value in there, it's just going to make a negative fraction. If you put a fractional value in there, it's just going to make a whole number. There's nothing that can go in here in an input that's going to produce an output of 0, which means that there's nothing that will ever produce an output of 0. So what we end up with is sort of this like cross-shaped no-no zone.
What's the no-no?
It's no-go zone. No-go zone. Anyway, we'll talk more about that when we go a little bit deeper into reciprocal functions. So the goal for you today would be to get a little flavor of what some alternate versions of these parent functions look like. And so what I'm going to do is I'm going to post on Google Classroom for you some inputs, some other examples. You need to find the outputs and plot the graphs. Now you have kind of a ballpark idea of what these graphs should look like. They're not going to vary too far from the parent functions because we're going to be transforming or changing these parent functions by adding in some math to them. Okay, so I'm going to go ahead and end the live instruction part there, and then I'm going to post this to Google Classroom. What I want you to do is find the outputs, plot them the way you think they go, draw the picture the way you think it's going to look, and then I want you to type the example into Desmos and check it and see if you got it right. Okay, that would be the way that you do the rest of the activity. Okay, all right. Give me just a second, and I'll post that to Classroom.